Imagine it is 3 o'clock in the morning. You're the on-call engineer. Your phone is just buzzing off the nightstand, and you groggily open your laptop.
Oh, we've all been there. The absolute worst way to wake up.
Right. So you connect to the VPN, and you see that your Kubernetes application is running incredibly slow. But here's the kicker. It isn't completely down.
Which honestly is almost worse to troubleshoot.
It really is. It's just bragging. Alerts are firing, the Slack channel is lighting up, and you are staring at a terminal prompt with absolutely no idea where the bottleneck is hiding. So, welcome to the deep dive.
Thanks. Glad to be here to unpack this.
Yeah, to figure out how to navigate this exact nightmare, we are pulling from a really massive stack of sources today. We've got the official KCNA curriculum, that's the Kubernetes and Cloud Native Associate Exam, plus several CNCF white papers on observability standards, and a few particularly brutal real-world postmortems.
Those postmortems are where the real lessons live, honestly.
Oh, absolutely. So our mission today is mastering Kubernetes observability. Because that 3 a.m. scenario, it perfectly illustrates why observability has transitioned from like a corporate buzzword to a critical engineering discipline.
Yeah, totally. Because when you move from a monolithic application to a distributed microservices architecture, you kind of lose that old ability to just SSH into a single server and read one big log file.
Right. You can't just grep your way out of the problem anymore.
Exactly. You need a system that can actually explain its internal state based entirely on its external outputs. And we look at the foundational concepts in that KCNA curriculum. They always start by establishing the core analogy.
The car dashboard.
Yes. Observability is the dashboard for your cluster. And before we get into any specific tools, you have to understand the 3 fundamental gauges on that dash, the 3 pillars of observability.
Right, the classic trio, metrics, logs, and traces.
That's them.
But, I mean, simply naming them doesn't really explain how they interact to solve an actual outage. So let's break down how they function mechanically, starting with metrics. Metrics are essentially time series data, right?
Right. You're looking at quantifiable measurements taken at regular intervals. Like CPU utilization is at 80%, or memory consumption is at 2 gigabytes.
Or, HTTP 500 errors are spiking to 50 per second. It's purely numerical.
Exactly. It's just numbers, which makes it incredibly cheap to store and super fast to query. Because they're highly compressible, metrics are basically perfect for your initial alerting logic.
So this is the speedometer and the fuel gauge. It's the trigger that actually wakes you up at 3 a.m.
Spot on. Metrics tell you that a system is failing. But numbers lack context, right? A spike in memory usage doesn't tell you which specific function caused the memory leak.
Right, you just know it's happening, not why.
Exactly. So that is where you shift to the second pillar, which is logs. Logs are discrete, high-fidelity records of an event that happened at a specific timestamp.
So this is the actual text output of the application, the warning lights on the dash.
Yeah. So if the metric tells you the database connection pool is exhausted, the log is the literal line of text from the app saying, connection timeout on port 5432.
Okay, but in a highly distributed system, I feel like logs alone still aren't enough. I mean, if a user clicks a button and that single request touches like 12 different microservices before it fails on the 13th?
Good luck trying to manually align the timestamps of 12 different log files across hundreds of pods. It's impossible.
Yeah, it's a nightmare. Which necessitates the third pillar, right? Traces.
Yes. Distributed tracing. This is the diagnostic port that tells the mechanic exactly which component is failing. It reconstructs the entire life cycle of a single request across all your network boundaries.
It records the path and breaks it down into segments, right? Spans.
Exactly. Each span tells you exactly how much time the request spent inside a specific service.
So to visualize how these interact for you listening, metrics are the radar telling you an aircraft is losing altitude. Logs are the cockpit warning system saying the left engine threw an exception. And traces are the flight data recorder showing you the exact sequence of events, from the fuel pump failing, to the pressure dropping, to the engine stalling.
That's a great way to put it. You really need all 3 to get a holistic view of the system's health.
Yeah.
Having just one is like driving a car with a speedometer but no check engine light.
Right. Okay, so that holistic view is what the CNCF standards are built to provide. But if I'm studying for the KCNA or just sitting at that terminal, how do we actually look at this dashboard? Before we install massive tools, we start with native commands.
Yeah, your first line of defense is just the Kubernetes API itself, access via Kubectl.
The native toolkit.
Yeah.
So let's start with Kubectl top. This pulls current CPU and memory usage, right?
Right, for nodes or pods. But here's a crucial detail for the exam. Kubectl Top doesn't just work magically out of the box.
Wait, it doesn't.
No, it relies on the metric server being deployed in your cluster. Under the hood, the kubelet on each worker node runs an internal component called KidVisor.
Oh.
Yeah, KidVisor gathers the raw resource usage from the container runtime itself. Then the metric server scrapes that data and makes it available to the Kubernetes API.
So Kubectl Top is just surfacing that real-time aggregated KidVisor data. But what if I need more context than just resource utilization?
Then you pivot to Kubectl Describe. When you run Kubectl Describe pod, you weren't just looking at a static YAML file. You were actually querying the Kubernetes Events API.
And the events section is usually where the actual forensic evidence lives, right? Like if a container keeps crashing.
Exactly. Kubectl Describe will surface the specific state changes recorded by the kubelet. So you might see an image pullback off because, I don't know, someone made a typo in the container registry URL.
Or an out-of-memory termination.
Right. And then for the third native tool, looking at the application output itself, you use Kubectl Logs.
Which just instructs the kubelet to read the standard output and standard error streams.
Yes. And a vital tip here, especially when you're actively troubleshooting, is using the AF flag.
The follow flag.
Exactly.
Yeah.
Kubectl Logs Best Use lets you follow the logs in real time as they stream in, rather than just getting a static snapshot of the past.
Okay, so let me ask a clarifying question here. If I can see metrics with Kubectl Top and events with Describe, and the actual text with Kubectl Logs, why do I need anything else? I've got the 3 pillars right there natively.
It's a fair question.
Yeah.
But the problem is that Kubectl is strictly ephemeral and manual. You're asking the cluster for its current state, or at best, the very recent past.
Ah, I see.
If a pod crashes and is evicted from a node, those Kubectl logs for that pod are just gone. The Kubernetes API is not designed to be a time series database.
It's an orchestrator, not a log aggregator.
Precisely. And more importantly, you can't have humans manually polling Kubectl 24/7 to ensure system health. Enterprise clusters need automated, persistent observation. The system has to observe itself.
Which brings us to the internal autonomic nervous system of Kubernetes, probes. This is moving from how humans observe the cluster to how Kubernetes itself observes it to keep things running.
Exactly. The kubelet continually runs diagnostic checks against containers using 3 primary probe types. And mechanically, it tests these in one of 3 ways.
Right. It can do an HTTP GET request.
Yep, looking for a 200-level status code. Or it can open a TCP socket to verify a port is accepting connections. Or, finally, it can run an exec command right inside the container namespace to check if a specific script exits with a 0 status.
Got it. Now, the sequence of these probes is heavily tested on the KCNA. It starts with the startup probe, right?
Yes, and it's important to understand why it's sequenced that way. Imagine you have a legacy monolith or a really heavy JVM application.
Oh, yeah. Those things can take like 2 or 3 minutes just to initialize, build caches, and finally connect to the database.
Exactly. If you immediately started pinging that app with standard health checks while it was still booting, they would fail.
And Kubernetes would kill it before it even finished starting.
Right, so the startup probe disables all other checks until it succeeds. It buys the application time.
Okay, so once the startup probe succeeds, it hands off responsibility to the Liveness and Readiness probes.
Yes, and those run concurrently, but serve entirely different functions. The Liveness probe asks a very fundamental question. Is the process inside this container deadlocked?
So is it alive?
Basically, if a Liveness probe fails repeatedly, the kubelet considers the container compromised and sends a signal to the container runtime to just restart it.
Okay, wait, this is a huge trap on the exam. I see this all the time. So if a liveness failure triggers a restart, a readiness failure just does the same thing, right? It just restarts the pod.
False. That is a massive trap. Mechanically, that makes no sense.
Okay, explain why.
The readiness probe dictates network routing, not container lifecycle. It asks, is this application ready to accept user traffic right now?
So the app might be perfectly healthy, meaning the liveness probe is passing.
Right, but it might be temporarily overloaded or doing a heavy background database sync. It doesn't need to be killed, it just needs a break.
So when a readiness probe fails, what actually happens?
The kubelet communicates with the control plane, which modifies the endpoints object associated with your service.
Oh, wow. So it actively removes the pod from the service endpoints?
Exactly. It signals kubeproxy on every node to update its iptables rules, routing all new network traffic away from that struggling pod until the probe starts passing again.
That is such a vital distinction. Liveness talks to the container runtime to restart the process. Readiness talks to the service endpoints to stop traffic.
You absolutely need to know that for the KCNA.
Okay, so we've covered the native tools and the internal probes, but what happens when we scale up, when we need that heavy-hitting, persistent historical telemetry?
Then you move to the CNCF industry standards. And for metrics, the undisputed standard is Prometheus.
Prometheus, okay, what makes it so special?
It fundamentally shifted how the industry approaches monitoring, largely because it uses a pull-based model.
Instead of push-based?
Right. Historically, you would configure every single server to actively push its metrics to a central monitoring server.
Which, I mean, works fine if you have, like, 50 static virtual machines.
Exactly. But in Kubernetes, you might have pods spinning up and terminating thousands of times a day. If they all pushed data, it would create massive configuration overhead. The central server would be bombarded by ephemeral IP addresses it doesn't recognize.
So Prometheus pulls the data instead. It's kind of like, okay, so instead of the applications constantly shouting out their status, which is push-based, Prometheus is like a teacher walking around a classroom, actively checking over the shoulder of every student to see how they're doing.
I love that analogy. That's exactly it. Prometheus actively talks to the Kubernetes API server to discover all the targets, the nodes, the services, the pods. That's its service discovery mechanism.
So it uses the cluster's own control plane as a real-time directory.
Right. And once it knows who is supposed to be in the classroom, it reaches out to the HTTP metrics endpoint of each target and pulls the data.
That is so smart. And then it relies on PromQL to actually query that data, right?
Yes, PromQL is incredibly powerful. You can calculate, say, the 99th percentile of request latency over a rolling 5-minute window, sliced by specific pod labels.
But PromQL just returns raw numbers, doesn't it?
It does, which is why Prometheus is almost universally paired with Grafana.
Ah, Grafana, the visual layer.
Exactly. Grafana queries Prometheus and renders those complex aggregations into those beautifully designed, customizable visual dashboards. Together, they are the standard stack.
Grafana is the actual dashboard you are staring at during that 3 a.m. pager duty. But wait, Prometheus and Grafana really only handle the metrics pillar. We still need logs and traces to understand the why.
Right, making sense of the mess. And logging in Kubernetes is notoriously difficult.
Because the container logs are ephemeral.
Exactly. When an app writes to standard out, the runtime intercepts it and writes it to a local JSON file on that specific worker node. If the pod dies or the node scales down,
Poof, the logs die with it.
gone forever. So centralized logging is absolutely required. You have to decouple log storage from the compute nodes.
How do you do that in practice?
Typically, you deploy a log forwarding agent, something like Fluent or FluentBit, as a daemon set.
A daemon set meaning it runs exactly one pod on every single worker node.
You got it. It constantly tails those local log files and ships them off to a centralized database.
And for the KCNA, we need to know the specific stacks here. There's the EFK stack, right?
Yes. Elasticsearch, Fluent, and Kibana. Elasticsearch is a beast. It performs full-text indexing on every single word in every log line.
Which sounds great, but full-text indexing is incredibly resource-intensive.
Oh, it requires massive amounts of RAM. If you are logging thousands of requests a second, your EFK stack can easily become more expensive to run than your actual production application.
That's wild. So what's the alternative?
The ecosystem has heavily shifted toward Loki, usually paired with Grafana. Loki takes a totally different architectural approach. Instead of full-text indexing, Loki only indexes the metadata.
The metadata, you mean the Kubernetes labels?
Exactly. The exact same labels that Prometheus uses.
Oh, that's brilliant. So if I'm looking at a CPU spike in Prometheus for a pod labeled, a payment service, I can just seamlessly pivot over to Grafana and see the Loki logs for that exact same label.
Exactly. It creates a perfectly unified workflow. Plus, the log streams themselves are just compressed and stored cheaply in object storage, like S3. It makes Loki incredibly lightweight compared to Elasticsearch.
Okay, so that handles logs. What about the third pillar, traces?
Right, tracking that single request, bouncing across dozens of microservices. The CNCF standard here is OpenTelemetry.
OpenTelemetry, how does that actually work mechanically?
It's all about context propagation. Imagine a user clicks checkout. The ingress controller gets that initial HTTP request. OpenTelemetry intercepts it, generates a unique trace ID, and literally injects it into the HTTP headers before passing it to the first service.
And then as that request jumps from the inventory service to the payment gateway to the shipping database,
the OpenTelemetry client libraries ensure that exact same trace ID header is passed along every single time. Every service records its own span of time, tagged with that ID, and exports it to a backend like Jaeger.
So Jaeger just stitches it all back together. You don't just see a 10-second checkout. You see a waterfall graph proving 9 of those seconds were spent waiting on a locked database table in the inventory service.
Exactly. It gives you the full picture.
Okay, so we've established the whole theoretical architecture. Let's put it to the test. How do these tools actually look in practice when things go horribly wrong?
Let's talk about resource limits, because that's what usually goes wrong. You have to understand Linux control groups, or C groups.
Right. When you define resource requests and limits in your pod spec, Kubernetes passes those to the runtime, which uses Linux groups to enforce them.
But the kernel handles CPU limits and memory limits very, very differently.
Because CPU is compressible, right?
Yes. A CPU limit just sets a quota on the completely fair scheduler. If a container tries to use more CPU time than its limit allows, the kernel doesn't terminate it, it just throttles it. It pauses execution until the next scheduling period.
But memory is incompressible. You can't just pause RAM.
No, you can't. If an app allocates memory beyond its C group limit, the Linux kernel has absolutely no choice but to invoke the OA killer.
The out-of-memory killer.
Exactly. It immediately sends a SIG kill to the process.
All right, let's apply this to 3 real-world KCNA-style scenarios. Scenario 1. We have a cluster experiencing severe network dropping. The pods show as running. The Liveness probes are totally passing, but users cannot connect, and the ingress controller is returning 502 bad gateway errors.
Okay, if the Liveness probe is passing but traffic is dropping, you immediately look at the Readiness probe. You run Kubectl describe pod to check the events, and you'll likely see a Readiness probe failure.
Right, and because of that, the endpoints controller dynamically removed the pod's IP from the service.
Exactly. The system is protecting itself from routing traffic to an overwhelmed pod.
Perfect. Okay, scenario 2. A pod is constantly crash looping. It starts, runs for 30 seconds, and terminates over and over.
A crash loop points to process termination. Natively, you run Kubectl, describe and look at the last state reason. If it says own killed, you know the application hit its memory limit and the kernel killed it.
And if it doesn't say own killed?
Then it's highly likely the Liveness probe failed due to a deadlock and the kubelet is restarting the container runtime.
Got it. Okay, scenario 3. We are back to our 3 a.m. nightmare. The application is incredibly slow, but it isn't crashing and it's not dropping connections.
Slow but stable execution is the absolute hallmark of CPU throttling. The scheduler quota is just holding the process back.
So natively, I'd see that with Kubectl top if the CPU is pinned exactly at the limit.
Yes, but for historical context, you would open Grafana, query the Prometheus metrics for CPU throttling duration, and you would see the exact moment the app hit its group ceiling and the latency spiked.
That makes so much sense. So whether you are staring at a KCNA exam paper or a broken production cluster, observability is simply about reading the telemetry.
It really is.
You use Kubectl for immediate manual investigation, probes for automated lifecycle management, Prometheus and Grafana for metrics, Loki for distributed logs, and OpenTelemetry for traces. It's a remarkably robust toolkit.
It's an incredible engineering achievement to build a system that can make sense of such immense complexity. But, there is one final architectural challenge that often gets overlooked.
Oh, what's that?
Well, as you build out these incredibly robust stacks, deploying OpenTelemetry sidecars, daemon sets for log forwarding, Prometheus scraping agents across thousands of nodes,
Yeah.
you start generating massive amounts of compute overhead just to watch the compute run.
Ah, the observability tax.
Exactly. You are generating terabytes of telemetry data. At a certain scale, the infrastructure required to monitor the application becomes heavier and more resource-intensive than the actual application you are trying to monitor.
Oh, wow. That's a huge paradox.
It is. If the Prometheus instance runs out of memory, or the logging daemon set starts dropping packets, your entire dashboard goes dark.
So how do you monitor the monitor?
That's the million-dollar question.
Yeah.
As you architect these systems, you really have to account for the weight of your own telemetry.
Definitely something to chew on the next time that pager goes off at 3 in the morning. Well, that wraps up our deep dive into Kubernetes observability. Thanks for joining us, and we'll catch you next time.